Alright, welcome to Chapter 8 video for physics class. This one is going to be about rotational motion and torque, which is kind of a new thing compared to chapters 1 through 6 that we've covered so far. Up until now, we've only looked at how forces cause things to accelerate in a linear path. It could be two dimensions, but still the object is just treated as an overall object. Remember, we drew everything as a box. And we didn't care about the actual shape of the object or whether it was rotating as it moved, just that the overall object was being translated side to side. So now in Chapter 8, we're going to start considering that the object itself, the shape of it and where you push on the object is kind of important. You know, if you push on a box in the center of the box, you'll get a different effect than if you push on a box on just one edge, like it will rotate versus move. And so to do that, there's a new physics concept called torque, and it will enable us to study rotational motion. Alright, here we go. So rotational motion intro. When you push an object, it tends to move in a straight line. Some examples of things where there's a pivot point where something is pinned down, leading to rotation, is these doors on like a classic old-fashioned bar. Even though you're pushing on them, they don't actually move forward. Instead, they rotate because there's also a force on the hinge that's holding them in place. And if the two forces are not directed along the same axis, the object will tend to rotate. Just try taking something in front of you, pushing forward on one side and backward on the other side, and you'll see right away what I'm talking about. Your knee is a great example of something pivoting. Tendons, this has a really huge application in biology, so if you guys are interested in med school or in human bio, like the way your tendons attach to your arm, to lift or lower your forearm or your shoulder out like this, all of that stuff is based on torque because you're causing a rotation around a pivot point. So it's really cool. I like this chapter. Your objects will rotate. This is all things I've said, some examples. And I'll insert a video either now or later, depending what looks best, with me pushing on a cereal box so you can kind of see, and you can try it at home in front of yourself, your keyboard or something like that. Okay, so if I push the box along the center axis, it should move forward but not spin. So if I push roughly right here, it will just move forward and not spin. And that's because the force of friction acts from the center of the object backward, and my force acts from the center of the object forward, and the forces are aligned with each other. But if I push on the box off axis, like over here, the force of friction is acting backward from the center, but I'm pushing forward from the side. So what happens is it does move forward, but it also tends to spin. So it's both translating forward because I'm pushing it, but it's also spinning because my force is not acting on the center of the object, it's out at some distance. So if you know the radius and the angle that you're pushing, you can figure out the torque that will tend to cause your object to rotate. So you can try this at home in front of yourself, just get a book or something. Depending on where you push, it'll rotate clockwise or counterclockwise. And we'll talk about the equation for that soon. Okay, so before we start looking at the forces exerted and the torques exerted that causes something to rotate, just like we did in chapters 3 and 4, we're first going to analyze, okay, suppose my object is actually rotating. Is it rotating faster and faster or slower and slower? That's called angular acceleration. So the rate of rotation could speed up or slow down. Instead of regular acceleration for speeding up and slowing down, it's angular acceleration. Likewise, how fast the object is rotating at any point in time is called angular velocity instead of linear velocity. And the position that it's in, this is a little bit tricky. Normally with position, you'll just look at distance traveled in meters. But when something is rotating, every time it rotates 360 degrees, it comes back to where it was. So we're going to look at the total angle rotated, which means, like, say it goes around 2 full revolutions. That would be equivalent to 720 degrees, except we're going to be using radians. So 1 full revolution is 2 pi radians. So 2 full revolutions would be 4 pi radians, etc. If you're not very comfortable converting between radians and degrees, let me know and we'll practice that a lot in class. But essentially, 2 pi radians is 1 lap around. So I've written that right here. 1 rotation is 2 pi radians. Another unit that's commonly used in this chapter and in general for things rotating is RPMs. RPM stands for rotations per minute. So you might have to convert rotations to radians, and you might have to convert minutes to seconds in order to get it in SI units and compare it to other SI quantities. The cool thing is, though, whether things are moving in a straight line or whether things are rotating, the relationship between distance, velocity, and acceleration is exactly the same, right? If you accelerate, you're going to be going faster, whether you're rotating or whether you're going in a straight line. So we had formulas before in chapter 3 that related distance, velocity, and acceleration, and we had 5 variables: vi, vf, d, t, and a. We're going to have those exact same equations with those exact same 5 variables, except now the d in the formula is going to represent the angle rotated. The vi and vf is going to represent the angular velocity, how fast it's spinning around. And the a in the formula is going to represent the angular acceleration. So if you take all those formulas and you change distance to theta, which represents angle, and you use radians, change all your v's to this symbol is the Greek letter omega that stands for angular velocity, radians per second instead of meters per second. And your acceleration will change to angular acceleration, and the symbol we use will be alpha, and radians per second squared instead of meters per second squared. Then you can use the same formulas as we had before, and you can solve a whole bunch of problems without really having to do any more work. So just as a reminder, so you don't have to pan back to chapter 3, if you wanted to recopy these down in this section of your notes, press pause, copy them down. You can either copy them down with the same variables we had before, or you can write new formulas by changing out d with theta, v with omega, and a with alpha. Personally, if I'm being honest, I actually keep using them in their old form with just regular velocity v, regular acceleration a, and regular distance d. And then in my head, when I'm plugging in angulars or angular velocities or angular accelerations, I know in my head that I'm doing angular motion. But it's just easier to use the formulas the way I've written them over and over and over before, instead of trying to get new ones. I just noticed right here, remember, x final and x initial are initial and final position. So sometimes I combine those together and I just write d equals vit plus 1/2 at squared. So that one might look a little funny, but that's why. Final position minus initial position represents distance traveled. Okay, so we're just going to jump right into an example problem using these new variables, but the same equations we had before. So here we go. An old-fashioned record player takes 3 seconds to get, quote, up to speed, which means that's how fast it should be going when it's playing the song. And it has an angular acceleration of 3 radians per second squared. How many rotations will it take before the record can play normally? So how many rotations will it take? That's asking us basically the distance traveled in terms of the angle rotated. And what is the final playing speed? So that's final velocity in RPMs. Okay, so they give us the acceleration in radians per second squared, and they're asking for the playing speed in rotations per minute. So we know we have to do some conversion factors there. So let's see, what does it give us? The acceleration is 3 radians per second squared. The time is 3 seconds, and the initial velocity is 0. Okay, so I've got some space to work this out. Let me bring up my little pen. Okay, so I knew that my v initial was 0, and here I'll write the right units, radians per second. I knew my time was 3 seconds, and I knew my acceleration was 3 radians per second squared. And they asked me to find the v final, and they also asked me to find the distance, which is an angle. So I'm going to write d theta, just so in my head I'm remembering I'm trying to find the angle that it rotated through. But again, this is just deja vu on chapter 3. We've got these variables and we're looking for this one. So the first simple formula is v final equals v initial plus acceleration times time. Plug in 0 plus 3 times 3. That's going to be 9 radians per second. Hey, that was pretty easy, right? That equals v final. And it said, though, let's verify, it said, let's find the final playing speed in RPMs. Well, hell, how do we convert radians per second into RPMs? We're going to have to multiply this by a conversion factor of 60 seconds is 1 minute. That will convert seconds into minutes. And we want rotations. And 1 rotation is 2 pi radians. Okay, so here's our 2 conversion factors. And I like to do it like this, kind of like chemistry class. Cancel my units, cancel my units. So I've got 9 times 60 divided by 2 pi. So that's around 270 over pi. I don't have a calculator, so you'll have to check this for yourself, but 270 over pi should be like, I don't know, a little less than 90, 85. I'll put like a little squiggle, something like 85 RPM, something close to that. Check it on your calculator, but the calculation is correct. Now we can say, how many times did that record rotate? What was the distance rotated, or how many degrees did it rotate? So what formula do you want to use? I don't know, an easy one would be VIT plus 1/2 AT squared. Again, VI is 0. Okay, plus 1/2 3, and then time was also 3. So this is half of 3 times 9, which is 27, divided by 2, which is 13.5. And what units are we using? Well, our units plugged in are radians per second and seconds. So this is going to come out in radians. So the distance that we traveled, 13.5 radians. If you wanted to know how many times the record revolved around, you could divide by 2 pi to convert radians to revolutions. It asks how many rotations will the record make. It does ask for rotations, so we need to convert this. So times a rotation over 2 pi. I don't know what that would be. 2 pi is roughly 6, a little over 6. So this is like, I don't know, 12 divided by 6 is around 2. So something like 2 rotations. Again, you can check the numerical values on your calculator, but if you have the setup correct, I'm sure you'll get them right. So I just want to reiterate that you can solve a whole bunch of these problems, and you'll solve them in the exact same way that you did Chapter 3, but now it's representing rotational motion instead of linear motion. All right. So we've pretty much taken care of all the motion that's going to occur, but now we want to analyze what gets things to rotate in the first place, what causes them to rotate rather than to just translate or move in a straight line path. And so this is kind of a big concept, and it's going to start off simple and quickly progress to some challenging problems where you get to really use a lot of the things that you've learned. So the title of it is called torque, and I'm sure any of you that are into cars, you know, they'll give you the amount of torque that the engine can output, which is what causes the tires to rotate, which is what causes the cars to go. But in general, torque is something that causes a rotation around a pivot point. So I like to think of it in my head as like a rotational force. You do something to something and you cause it to rotate. So a force would cause something to accelerate linearly. A torque will cause something to accelerate rotationally around an axis. But strictly speaking, in terms of physics, torque is not a force. The units are not newtons, and so it's not actually a force. But conceptually, it might help if you think of it that way in terms of causing a rotation. So the mathematical formula for torque is RF sine theta, and the units are the units of radius are meters, and the units of force are newtons. So the units are newton meters. A newton times a meter is the unit of torque. The R in the formula stands for the distance from the pivot point to where the force is applied. So what that means is if you increase the radius, you increase the torque. So if you're trying to push on something to cause it to rotate, the farther you are from the axis of rotation, the more torque you exert, which means it's going to be easier to get it to rotate. Just think about opening a classroom door, right? If you push right next to the hinge, you have to push really, really hard to get it to open. But if you push far away by the handle, you don't have to push nearly as hard because your radius is a lot larger, therefore your torque is a lot larger. Okay, F is the value of the applied force, so obviously if you push harder, things will rotate faster. And theta is the angle between the force vector and the line from the pivot point. So I need to draw a little picture for this one. So suppose here's my hinge, or pivot. And then say I've got a door. Okay, the radius is the distance here from the pivot to where I'm pushing. And then say I'm pushing this way with some force. I'm pushing this way with some force. The angle here is the angle in between these two vectors. So you have to kind of keep this line going. Then that right there is the angle. So that's kind of cool. You can draw these pictures and you can figure out the angle that will maximize or minimize your force. So now look at this real quick, sine theta. If you push at a perfect right angle, then this angle is 90 degrees. and if you practice your trig, you'll know that sine of 90 is 1. So, and that's the biggest sine will ever be. So you're going to get the maximum torque, you're going to get the maximum rotation if you push perpendicular to the object or the radius from the pivot point to where you're pushing. So you always want to push at a right angle. And you know this intuitively, like when you try to go open a door, you push perpendicular to the door and it opens. If you push obliquely or slanted off to the side like this, if you push like that on a door, it will open, but not nearly as well as if you would have pushed here, because in that case, the angle between the force vector and the radius vector is a lot smaller, and sine of the smaller angle is going to be less than 1. Therefore, the total torque output will be reduced. So, moral of the story, push far away from the pivot point, push really hard, and push at a right angle, and that will maximize the torque, which will cause the most rotation. So if you're trying to get something to rotate, those are the 3 criteria you want to fulfill. Now, note, diagram is important. Because where you push relative to the pivot point affects both the distance away that you plug in for the radius, and also how you draw it will affect the angle. You need to make sure that your picture is inclusive of all these factors. So whereas with a force diagram, you just draw a box and you label all the forces coming off of it, if you're looking at a torque diagram, which includes rotation, you actually need to draw the object, not like a super artist rendition of some, cat or whatever, but you need to draw it elongated so that you can show what the pivot point is and where the force is applied and what that distance is in between them. So your force diagrams or your torque diagrams, they'll be a little bit more extended and cool looking, and if you fancy yourself an artist, you're welcome to try to spend a little extra time to make them look cool. I'll certainly appreciate that when I'm looking them over, but it won't affect your answer at all. So choose your pivot point and label the forces at their actual location. That's really important. And this choose a pivot point is also pretty important because you can't figure out how far away something is from the pivot point, which is what you need for this variable right here, unless you've drawn and labeled a pivot point. So that's pretty important as your starting point. Draw and label a pivot point, and then everything else will be a lot easier from there. Some nice pretty pictures just to motivate and make you agree with me. Hopefully this will force you to agree with me if you didn't already, that learning how to do torque is pretty important and useful for a lot of daily applications. Anytime you ride a bicycle or anything that's got chain links on it, this is a fantastic example of torque. The radius right here is not the same as the radius back here, which is why when you change gears it gets easier and harder to pedal. As you adjust the size of this gear and the size of this gear, you're messing with the radius, and as you see in this formula, if the force goes up, another way to say it is, if the radius goes down, the force goes up, and if the radius goes up, the force goes down for a certain amount of torque output from your bicycle. So to make it easier to pedal, you want to make the radius on the gears larger in front, and if you want it harder to pedal, or if you want to go faster, you make the front one a lot smaller. If you go fly fishing or any kind of fishing, you are rotating this length right here from here to here. That length is the radius around which you're rotating. So if you catch a really big fish, you might want to make this longer so that you have a larger radius and therefore more torque to crank it up and get that guy to come in. A propeller rotating around on an airplane. All these are examples of torque. Here's a little picture. You've got a little fulcrum, which is basically a seesaw or teeter-totter. It's rotating around a pivot point right there. So they label it as a fulcrum. I would call it a pivot. I always just say pivot, but fulcrum means the same thing. You can label the direction of rotation. That's usually a good idea. And you want to actually label positive and negative. I'll talk about that pretty soon. They label the distance from the pivot over to the force, and then label the force, and then of course they label the angle. So all of the important things are labeled. Let's take a sample problem about torque and see what we can see about calculating some values. How much torque is needed to unscrew a bolt that has a radius of 1.2 centimeters and is held tight with a friction force of 950 newtons? How should we hold the wrench to maximize our torque? Let's answer this question first because it's easiest. How should we hold the wrench to maximize our torque? We should hold it perpendicularly with our hand, so that when we push perpendicular to the handle of the wrench, because that's the radius, and we want to keep the right angle there. So let me draw a little picture real quick on the next slide. Radius is 1.2 centimeters, friction is 950. So radius is 1.2 centimeters, and the force of friction is 950 newtons. So pretend there's a little bolt in here that we're trying to unscrew. Lefty-loosey, righty-tighty, so that would be tightening it, that would be loosening it. So we are going to put a force this way, and we should hold it, so that's 90 degrees. Okay, that will maximize our torque. So the distance here, from the pivot point out to the end, that's our distance. This bolt right here has a radius of 1.2 centimeters. So the friction on the bolt is acting here at the radius. The force that we're applying is way out here. So you can see that the friction is acting at a small radius because the friction is right here around the bolt itself. Friction is acting at a very small radius, and we're applying a force at a very large radius. So since our distance is bigger, the force that we need is a lot smaller. Okay, so what is it actually asking us for? It's asking us how much torque is needed to unscrew the bolt. So actually, for the torque of the bolt, oh, I screwed up. Torque is not T. Cancel, cancel, cancel. Torque is tau, which is like that. The torque of the bolt is R of the bolt times the force of friction on the bolt. Notice these are always on the bolt. Force on the bolt, radius of the bolt, times sine of the angle on the bolt. This is a little bit tricky, angle on the bolt, but the R and the F are not. So 1.2 centimeters. Let's convert centimeters to meters by dividing by 100. Yikes. 100 centimeters is in 1 meter. Centimeters cancel centimeters. Okay, times 950 newtons. And I'm going to talk about this real quick. Anytime you have friction acting on a spherical object that's rotating, the friction is perpendicular to the radius. So let's like microscopically zoom in on this part. So zoom in on that. Here's your bolt, okay? And here's the edge of the whatever it's screwed into. Okay, when this thing tries to rotate, right, friction opposes rotation, or it opposes any motion. So if this thing is trying to rotate this way, friction is going, at this point, say, friction is going to point this way, opposing that. So there's your force of friction. But here's the center of the bolt, and here's the radius. So friction is always tangent to the edge of the circle that's rotating, and tangent is by definition perpendicular to the radius. So this angle for friction of a rotating object is always going to be 90 degrees. So that's 90 degrees, and sine of 90 degrees is a 1. So you basically don't have to include that part if it's 90 degrees because the whole thing just disappears. So the torque on the bolt is, I don't know, 950 divided by 100. That's 9.5 times 1.2. Yikes, I can't do this in my head, I'm too tired. Type it in your calculator and get an answer. And that will be the torque, tau, on the bolt. Fantastic. So if we wanted to unscrew this bolt, because our radius is a heck of a lot bigger than the radius of the bolt, the longer this wrench is, the less force we need. Okay, so let's go back and see. There's a second question here. If we hold the wrench 45 centimeters from the pivot point, how much force do we need to apply? Okay, so the torque of us should be greater than or equal to the torque of the bolt. So in order to get that thing loose, we have to exert at least as much torque as what's holding it in place. But the torque of the bolt we already found out is some number, right? That's your answer right here. Plug that in right here. The torque that we apply is the radius of us times the force of us, greater than or equal to. So let's just say equal to, just to barely get it moving. Torque on the bolt. So 45 centimeters, you're going to put that in right here, 0.45 meters. Okay, plug your answer from the previous problem in right here, And then how do you get the force that we apply? Divide both sides by 0.45 meters. Okay, so again, you can see that the bigger the radius is, you're going to end up dividing both sides by this value, right? So the bigger the number that you put here, the bigger you're dividing by, therefore the less force you need. The farther away you push, the less force you need. Very cool. Notice, I can't make this any more obvious. Larger radius, less force. So there's our worked out solution. All right, check for understanding. Let's check this one real quick. Unfortunately, we can't do this as a class because you're at home on your computer. But pretend that you are in a class setting. You can argue with your parents about this or something fun. A mechanic is finding it very difficult to muster enough torque to twist the stubborn bolt with a wrench, and he wishes he had a length of pipe to place over the wrench handle to increase his leverage. So what he wishes he had is a big pipe that he could put on it like this, so that instead of pulling here at a small radius, he could pull up here at a much larger radius. And he's a pretty smart guy, you know. He knows that if he puts a pipe on there, it'll make it easier. He doesn't have a pipe, but he does have a rope. So he ties the rope on here and extends it, and he pulls way over here, much farther away. The question is, will his torque be increased if he does that and he pulls with the same force? So pause the video, take a moment to think about it, unpause the video, and watch my answer. The answer is a big fat no. Okay, so if you know why, maybe you can skip the explanation, but if you want to see the explanation, here it is. When he pulls right here, all that does is it translates the force through the rope, 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 through the rope right here. The tension in the rope here is the same as the tension in the rope here. And remember, we said forces have to be either long range, which is gravity, or they have to be contact. Okay, he is not actually touching this wrench. What's touching the wrench? The thing that's pulling the wrench is the rope. And the rope is pulling it in the exact same place his hands were. So he's pulling the rope is pulling the wrench, and the physical location of contact is right there. So the radius that the wrench feels, as far as the wrench can tell, it's getting yanked on right here, which is the same exact radius as before. It makes no difference that he added the rope. Kind of exciting, yeah. All right. Let's combine torque and motion. Just like chapters 3 and 4, we first learned chapter 3 on motion, then we learned chapter 4 on force, and then we tied the two together. So with linear force and motion, we tied the two together with Newton's second law, F net equals ma. So there's a very similar law which explains how torque, which is like a rotational force, causes rotational motion. So when you put a torque on something, it's going to start to rotate. But exactly how is it going to start to rotate? So we used to have F net equals ma. Now we have torque net equals I alpha. Well, you know that force is like torque, and you know that angular acceleration is a lot like acceleration. So what the heck is this I right here? This I is kind of like mass, but it's like an angular mass. It's a little bit strange. So with F equals ma, the heavier the object is, if you push on it, the harder it is to get it moving, right? Well, this I thing is like that, except it's talking about rotation. The bigger the value of this I variable, which is called the moment of inertia, the bigger the inertia of this object, the bigger the moment of inertia, the harder it is to get it to rotate. So there's a couple of things that go into the moment of inertia for object. It certainly depends on the mass. The heavier it is, the harder it is to rotate. But it also depends on the shape of the object. Some things are easier to get rotating than others, and it depends on how far the mass is from the axis of rotation. So if the mass is clustered near the center, it's going to be a lot easier to get it spinning. Here's an example. Think about having this pen. I hope it shows up in the video. If I rotate it this way, it's pretty easy to rotate this way really rapidly, because the particles don't have to travel very far. They're just going around in little circles, so it's easy to get them moving. Spin, spin, spin. But if I try to rotate the pen this way, the particles on the end, they're tracing out, like, as they go around, they're going a long ways. So it's going to be a lot harder to get them going because they're going to have to travel a lot farther distance, which means either they have to go faster or my rotation is going to be a lot slower. So it's harder to get something rotating if the mass is far away from the center pivot point. It's easy, or on axis this way, it's easy to get it rotating if the mass is close to the axis of rotation. So in your book on page 206, there's a table of the values for the moment of inertia for different shapes. We're not actually going to do much calculation with this, but as a concept you should know the formula torque net equals I alpha. So if I just give you a numerical value for the moment of inertia, it's kind of like if I just gave you the mass of the object. Then you should be able to use this equation to calculate the acceleration or the torque exerted. But I won't say find the moment of inertia for a certain shape. So you won't need to memorize any of these formulas on 206, but you can take a look at them if you want and kind of get an idea of how the rotational ease for an object depends on its shape. Alright, we're getting close. This is the last big hurdle. It's also a good place to take a break if you're getting a little burned out or want to, get some water, take a break, run around, stretch, etc. This last one is the most mathematical, and so I'll go through it as quickly as I can, but it's a little bit of a beast. So, static equilibrium. We already have learned about regular equilibrium. That means the net force is 0. But even if the net force is 0 and an object is not moving, it could still be rotating. And typically when you think of something in equilibrium, you think of no motion whatsoever. So we're kind of upgrading our equilibrium, regular equilibrium, to static equilibrium, which means the object is not sliding around and it's also not rotating. I have to modify what I just said. If the net force is 0 and the object is in equilibrium, it doesn't necessarily mean it's not moving. It means there's no change in motion. It's not accelerating. So if it was already moving, it will keep moving. And if it was at rest, it will stay at rest. And if the net torque is 0, it's not that it's not rotating. There's no change in rotation. So if it is spinning, it will keep spinning at the same rate. It won't speed up or slow down its spin, and it won't speed up or slow down its motion. So let me think of not a perfect example. Actually, not a good example at all. I was going to say a football spiraling, but it's definitely being accelerated by gravity. So off the top of my head, I can't think of a good example of something in static equilibrium that's moving but still in static equilibrium. Anything at rest is in static equilibrium, but to be moving with constant velocity and with constant rotation, I don't know. I'll think of it, and if I get one, I'll tell you later. So let's move on. A cool example that's frequently used is any kind of teeter-totter. So you got forces on one side, forces on the other side. The forces will balance out, but also if it's not tilting, then the torques will balance out. So we'll do examples something like that. Next one. This is kind of a long 8-step process, but it's really important that you don't leave any of these steps out. You don't have to memorize the steps, but you do have to make sure you include all of the pieces. So whatever works best for you. I would highly recommend writing them down at least once, though. So I'll go through them and then I'll apply them to a sample problem. Draw your extended diagram. That's a no-brainer. That's the first step all the time. Draw your picture, and by extended I mean not a box anymore, but actually kind of show the shape of the object, because where the forces are applied will matter. Label your pivot point. That's very important. Define positive and negative directions for torque as clockwise or counterclockwise. Just like when we had motion linearly, you had to say which way is positive, which way is negative. Now that things are rotating, you should choose clockwise or counterclockwise to be positive or negative. So typically you'll have your point and labeled pivot. And then I like to go something like this. I draw an arrow, double-sided, curved, and I might say something like positive, negative. So anything that causes rotations that way, which would be counterclockwise, I'm going to call positive. Anything with rotations clockwise, I would call negative. And so, you could change which is positive, which is negative. Doesn't matter whether you choose clockwise or counterclockwise. But some little arrow like this with a positive and negative label will really help you keep track of whether your torques are positive or negative. Okay, label all your forces. That's a no-brainer. And label all your distances. Label all your angles. So these 3 things are all just regular torque problems. I mean, anytime you have a torque problem, you got to have not only the forces, but also the distances and the angles. And that's, of course, because, don't forget it, torque equals RF sine theta. Very important. RF sine theta. Okay, once you have your full diagram with all your forces labeled, all your distances labeled, and all your angles labeled, you can write your net torque equations. And if it's in static equilibrium, right, net torque equals 0. Also, net force equals 0. Although you'll typically have to branch this into 2 possibilities. The x direction and also the y direction. So, believe it or not, in most of these problems, you can have 3 equations. You can have the horizontal forces equal 0, the vertical forces equal 0, and the rotations clockwise and counterclockwise equaling 0. So 3 equations, 2 force equations, 1 torque equation. So how many unknowns could be in your problem? Holy smokes. You can have problems with 3 unknowns. So you have a system of 3 equations, 3 unknowns. Am I going to be a real mean person and make the math super hard for you? Probably not. But be aware that that is a possibility. Maybe if you're in honors or something, or taking this class for math, which if you're in honors you are. Alright, so here's a not as complicated problem. You're in push-up position. Okay? Pretend you're flat. You are 2 meters tall. Your mass is 70 kilograms. Your center of gravity is at your midpoint. Your hands touch the ground 0.3 meters from the top of your head. Draw a picture, label all of our stuff. So, blank slide, here we go. Here's a person. Here's his head. Here's his feet. Here's his hands touching the ground. Okay, so it said 2 meters. That's the total distance. So we label that. It said, your hands touch the ground 0.3 meters from the top of your head. So that means this distance here is 0.3 meters. It says your center of gravity is in your midpoint. So where's your force acting? Your force is acting here. There's force of gravity. And how far is this going to be? Since it's acting in the middle, that's going to be 1 meter. Let's choose our pivot point. When you do push-ups, it seems reasonable that you could choose your pivot point to be your feet. Oopsie. P-I-V-O-T. Let's choose some directions for our torque. I like down to be negative and up to be positive. That seems reasonable. We've got the distance to the force of gravity labeled. We've got the distance for the whole thing labeled. We've got the distance to the hands labeled. Although, I've labeled this as 0.3, right? But the rule is you have to label the distance from the pivot point. So I also need to label this distance here. And of course that is going to be 1.7 meters. Because this total is 2 and this is 0.3, and if you subtract them you get 1.7. We have to label the rest of the forces though. So again, when you're drawing a force diagram, you ask yourself, long range force, yes, gravity in there. Second thing you ask yourself is my object touching anything? So when you're in push-up position, think about it. You're on your hands and your feet in a push-up position. What are you touching? You're touching the ground with your hands. So you're pushing down on the ground with your hands. Therefore, the ground is pushing up on you. So there's a force right here. F up on your hands. So I'm just going to write F hands. What else is touching you? The ground is touching your feet. So force up on your feet. I'll call that force on your feet. And let's pretend you're super, super awesome and you can hold a perfectly flat push-up. Then this is a 90-degree angle, this is a 90-degree angle, and this is a 90-degree angle. So we've got the pivot labeled, 3 forces labeled, 3 distances labeled, a positive and negative direction labeled, and we're ready to proceed and actually calculate some stuff. So what do we know about this guy? He's 70 kilograms. That's the only thing we know. We're supposed to find the force from the ground on our hands and the force from the ground on our feet. So we're supposed to find this one and we're supposed to find this one. And this dude has a mass of 70 kilograms. Let's see what we can figure out. Okay. F net is supposed to equal 0 if it's in equilibrium. What's F net? We've got the upward force of the feet and the upward force of the hands. Those two are both upward, F feet, plus F hands, minus the downward force of gravity, equals 0. There's one equation. Force of gravity is mg, which is 70 times 9.8. I don't have my calculator with me, so you'll have to type that in and get an answer. Okay, let's do our secondary equation. Torque net equals 0. Okay. There's 3 torques, 1 from each force, right? So you have to see this force here is trying to cause, actually let's start with the feet so I can line these guys up. The torque from the feet. The torque from the feet is right here. Would that be causing it to go clockwise or counterclockwise? It's actually kind of ambiguous. This force is acting at the pivot point. So in your formula, you have to remember, I'm going to write it over here. In general, torque equals Rf sine theta. So if the force is acting at the pivot point, your radius is 0. This is really cool. Any force acting on your pivot point has a 0 radius and therefore 0. So the torque of the feet is actually 0. Okay, let's go torque of hands. Torque of hands. Okay, if your pivot point is right here, and there's a force upward on you, it's going to take your whole body, hang on, the camera's reversed, it's going to take your whole body and angle it up like that. So you would be rotating in the positive direction, therefore this is a positive torque. You can't just assume that a positive here means a positive here. You have to actually look at it and see if the rotation is this way or this way. Okay, let's look at gravity. So here's gravity pointing downward. If this force acted on you, your whole body would tend to rotate downward this way, which we've chosen to be negative. So minus the torque of gravity equals 0. So you've got one equation here, and you've got one equation here, and you've got two unknowns. We already found out the force of gravity. That one is now known. So our two unknowns are the force on our feet upward and the force on our hands upward. Okay, so how can we figure these guys out? In place of torque of our hands, we need to put in R of our hands, F of our hands, sine angle of our hands. So what's the radius to our hands? Bam, 1.7. Okay, force of our hands, that's unknown. And what's the angle? The angle is 90 degrees, and therefore sine of theta is just 1. Okay, minus. This one we have to put R, F, sine theta, all corresponding to gravity. What's the radius for gravity? Gravity is acting in the center, which is 1 meter away, so we put in 1. The force here is the force of gravity. Whatever that value is, put it in right there. So I trust you to finish this guy off. Equals 0. Put in the value right here that you got right here, and then solve for F hands. Divide, like move this over to the other side, divide both sides by 1.7, and you can get the force on the hands. Okay, once you know the force on the hands, you're going to have to finish this one on your own. Plug the force of the hands in right here, plug the force of gravity in right here, and then in this equation, the only thing you don't know is the force on the feet, and you can move these two to the other side, and you can find the force on the feet. So pause the video, try to finish this exercise, take a few minutes. By the end of it, you should have calculated the force of the hands upward and the force of the feet upward. The sum total of those two upward forces should be equal and opposite to the downward force of gravity that you found right here. Conceptually, which one should be bigger, force on the feet or force on the hands? Just by looking at it, you can tell the force on the hands should be bigger because it's closer to the center, so it's supporting more of your weight. As a conceptual way to think about it. If you have this, the closer you are to the center, the more weight you support. Just try getting in push-up position and move your hands to various places. If you put them right under your midsection, you're going to have to support your entire weight on your hands, and your feet will basically be hovering. If you put your hands way above your head, then your hands and your feet are going to be balancing the weight roughly equally. Okay, slide ahead. Chapter 8 summary. At long last we have survived. So, for the rotation stuff, again, use the same equations as Chapter 3, but swap out distance, velocity, and acceleration for the angular counterparts. For torque, if it's just torque on a single object, use the formula Rf sine theta. R is the distance from the pivot to where the force is applied. F is the force, and theta is the angle in between the radius vector that you drew in and the force vector. If there's multiple torques on an object, you can add them up to get the net torque as vectors, and that will cause an angular acceleration according to the moment of inertia, which tells you how much the object resists rotation. And finally, if an object is in equilibrium, so there's no change in velocity angular and there's no change in velocity linear, the net force is 0, which will give you two equations, one for vertical, one for horizontal, and the net torque is 0, which will give you a third equation that allows you to solve for three unknowns. It could be unknown forces, could be unknown distances, could be unknown angles even. So it's there's a lot of variety in the type of problems that you can get. Alright, I hope this video made sense. Good luck trying the homework. If you're struggling, send me some emails. I might try to make another video with more examples. We'll see how it goes. Alright, see ya.